So, here is one more simple problem on pure rotational motion. You can say it is on rotational kinematics, not dynamics. Like a fan is rotating and you know its initial angular velocity, you know its final angular velocity, you are supposed to find out the angular acceleration. Fine? Okay, so let me read the problem. A rotating wheel changes angular speed from 1800 rpm to 3000 rpm in 20 seconds. What is the angular acceleration? So, I hope you remember the equations like v equal to u plus at, which we were using in translatory motion. Similarly, a replica of that can be used here in pure rotational motion, and that happens to be like this: omega equal to omega naught plus alpha t. But remember, v equal to u plus at was also used only when the acceleration was uniform, and omega is equal to omega naught plus alpha t should also be used only when angular acceleration alpha is uniform, and he has assured you that, assuming it to be uniform, he says. So, but remember one more thing: omega, alpha, they have to be in radians per second square and radians per second. Omega has to be in radians per second, alpha has to be in radians per second square. So, if you convert this 1800 rpm, which is nothing but revolutions per minute, and remember one revolution is 2 pi radians. So, if you convert this into radians, you get 60 pi radians per second. And similarly, if you convert 3000 rpm into radians per second, you will get 100 pi radians per second. Fine. So, you have already converted them, just substitute, get the value of alpha. So, what you get is 100 pi minus 60 pi would make it 40 pi is equal to alpha, time taken is 20 seconds. Therefore, alpha is 40 pi by 20, which is nothing but 2 pi radians per second square. So, that makes the third option perfectly correct. So, C option is correct there. So, one more very simple problem here, wherein he is just trying to check whether the student knows how to write the kinetic energy of a particle and how to write the kinetic energy of a purely rotating body like a fan. I think I might have told you earlier in the beginning of this particular session that kinetic energy of a body which is purely rotating is written as half I omega square, where I stands for the moment of inertia of that body about the axis of rotation and omega stands for its angular speed. So, half I omega square is how you write the rotational kinetic energy. Now, if it is a particle, then it has got only translational kinetic energy associated with it, which I think you have been writing as half mv square. So, now let us read the problem and see how we can use this. A body having moment of inertia about its axis of rotation 3 kg meter square is rotating with angular velocity omega equal to 3 radians per second. Kinetic energy of this rotating body is same as that of a particle of mass 27 kg. What is the velocity of that particle? That is the question. So, our job is to only write the two kinetic energies, equate them and get the velocity. I will do that. So, half I omega square should be equal to half mv square. So, half gets cancelled and you have I omega square equal to mv square. I about the axis of rotation is given to be 3 and omega about the axis of rotation is also given to be 3. So, that makes it 3 into 3 square is mass is given to be 27 and v square we do not know. So, now this 27 and this 27 will get cancelled and you get v square equal to 1 or v equal to 1 meter per second. So, the velocity with which that particle of mass 27 kg should be moving is 1 meter per second, and that makes the first option as the right option. See, now let me again remind you about how to write the kinetic energy associated with a particle or with a body which is exhibiting combined rotation and translation. And what was the relevant example that I had given you was the wheels of a vehicle which is moving on the road. See, they are rotating about the axle and the whole vehicle is translating on the road. So, there are two types of kinetic energies associated with that particular wheel. One is the rotational kinetic energy and the other is the translational kinetic energy. Translational kinetic energy has to be written as half mv square and rotational kinetic energy has to be written as half I omega square, where I stands for the moment of inertia of the wheel about the axis of rotation. Fine, let us read the problem and see how we can connect this with the present problem. A solid sphere of mass m rolls down an inclined plane without slipping, starting from rest at the top. The linear speed at the bottom is given to be v. The kinetic energy at the bottom is to be found. So, here there are a few things which you have to underline. One is, he says it is a solid sphere. So, that will really help us write the moment of inertia, and moment of inertia of a solid sphere about its axis of rotation would be half I omega square, and that would be 2 by 5 mr square would be the moment of inertia. Rotational kinetic energy would be half I omega square and I can be written as 2 by 5 mr square. Now, what he means by linear speed at the bottom can be taken to be the speed of the center of mass of the sphere. So, translational kinetic energy can be written as half mv square, and no slipping is another word which you have to underline, because had it been slipping we could not have conserved the energy. Because there is no slipping, there is absolutely no loss of energy between the transfer of that solid sphere from the top to the bottom. Half mv square is the translational kinetic energy plus half I omega square is the rotational kinetic energy. Now, I will substitute the value of I as I said. So, it is half mv square plus half I can be 2 by 5 mr square, because it is a solid sphere there, into omega square, and omega is nothing but v by r, because it is coming without slipping. And when there is no slipping, please remember the correct definition of no slipping. The point of contact of the body with respect to the surface should be at rest with respect to the surface. Therefore, I have written v by r as omega, so v by r whole square. So, that makes it half mv square plus 1 by 5 mv square, which is equal to 7 by 10 mv square, and that is C option. Okay, now let us see how we can omit a couple of options there. He has told you that the linear speed at the bottom is v. So, which means the translational kinetic energy itself is half mv square. Now, in addition to this, there has to be some rotational kinetic energy associated, which makes it more than half mv square. So, naturally first option would be wrong and the last option would also be wrong, because first option makes it 0.5 mv square and the last option makes it 0.4 mv square. So, two of the options can be straight away ruled out, and the correct answer that we are getting is, and that is C option. Now, let me brief you something about conservation of angular momentum, or let me first tell you how to write the angular momentum. See, for a particle, angular momentum is written as r cross p, where r is the position vector of the particle about some reference and p is the linear momentum of the particle, and for a body it is written as I omega. Fine. And now, what is this principle of conservation of angular momentum, or when should we really conserve? The principle of conservation of angular momentum says that in the absence of an external torque about a particular axis, the angular momentum about that axis remains constant. Fine. Okay. Now, if you read the problem, I hope you will understand how is it a problem based on conservation of angular momentum. A person is sitting firmly over a rotating stool and has his arms stretched. If he folds his arms, his angular momentum about the axis of rotation. See, please do not get confused as to he has asked the angular velocity, because that is a very popular problem. He has initially his arms stretched, so moment of inertia is more and the angular velocity might be less. Now, he folds his arms, thereby reducing his moment of inertia, because of which the angular velocity will increase. No doubt about that, but he has not at all questioned you about the angular velocity. He has only questioned you about the angular momentum, and which according to our principle should remain conserved or should remain unchanged. Therefore, the correct answer here is remains same. Okay, so in the previous few episodes, I think the chapters that we discussed were motion in one dimension, two dimension, and then Newton's laws of motion, and then work energy power, and then finding of moment of inertia using parallel and perpendicular axis theorem, how to deal with rotational kinetic energy, translational kinetic energy, and all those. And even we had one episode on moving charges and magnetism also, and I thoroughly believe that you must have enjoyed all these episodes, and that must have really given you a simple insight into the subject. So, I am Sunil Deshpande from Bijapur, and my sincere advice to all you people who want to give this CET for the coming year would be to just go through all the previous papers and try to analyze all the solutions for them. So, that will be really I think beneficial as a last minute preparation. So, all the best for you people, and thank you very much.